What's up, folks? This is Rev Bari, Brown University physics graduate student, bringing to you another lecture of advanced quantum mechanics. Now, so far, the math and physics have both been pretty simple, pretty straightforward. And if you think that quantum field theory is a joke, well then buckle in, because from today, the math is going to start to get pretty tough. So, where did we leave off in the last lecture? In the last episode, we looked at the action principle, which said that out of all the possible paths between 2 points, A and B, a beam of light would take that path which has the least action. Or in other words, as Fermat said it, the path which would take the least amount of time. Now, we looked at this problem from an energy perspective. We looked at the kinetic energy for a particle traveling from A to B and the potential energy. So let's write those down. The average kinetic energy would simply be 1 over the total time of the journey times the integral from 0 to tau of 1/2 mv squared. Okay, pretty straightforward. That's the average kinetic energy. Likewise, the average potential energy is 1 over tau, the integral from 0 to tau of t. Okay, so we've got the average kinetic and potential energies up here. So we were analyzing this problem from that perspective, from a conservation of energy approach. But the question that we failed to answer in the previous episode is, what would change if we perturbed the true path by a little bit? In other words, if we didn't go the path of least time, but a path that is slightly off the true path, a path that is slightly deviated from the true path, then how much would my kinetic and potential energy change? Let me repeat that question, because that is the central question that we're going to spend this entire episode addressing. What we're going to address in this episode is how much does the kinetic and the potential energy of a classical particle change as we perturb the path of least time or the path of least action. Okay, another way to say that is, let's say I have two endpoints, point A and point B, and I know that a particle, a classical particle like a ball, might travel the path of least action. Let's call that path Q. Okay, now if I perturb that true path, that path of least action, by a little bit, then I get this new path, let's call it Q prime. The question is, how much does the kinetic and potential energy of my particle change if the particle travels through Q prime rather than Q? That's the question. So to answer that question, we need to turn to the calculus of variations. That is the theory, the mathematical theory, that deals with not functions, but functionals. Functions which are functions of functions, functionception. Let me recap what functionals are for the unacquainted viewer. Recall that a function is simply a machine that takes in some kind of a real number input and spits out a real number output. So for example, x squared is a parabola, takes in a number and squares it, right? Takes in a real number, outputs a real number. A functional, however, is qualitatively different. A functional accepts a function as an input, so it's going to accept a function as an input and return a real number. So even though the outputs are the same, the input for a functional is a function, not a real number. That's the key difference. A functional is a function of a function. Now, the most basic functional is just an integral, right? A definite integral. Let's take a look at a basic example. We looked at a few examples yesterday, but I'm not going to recap them. I'm just going to summarize the results from the previous lecture, which is why you should watch the previous lecture if you haven't already. But the most simplest kind of functional is, for example, let's say j of f of x. Okay, now notice that I'm using these square brackets here to indicate that this is not a function, it's a functional, and this is equal to some kind of a definite integral. Let me just pick some arbitrary numbers. All right, so there you go. We've got a definite integral up there. That's the simplest example of a functional. for instance. And let's just plug something in. For example, if I had j of x squared, then this functional would evaluate to x squared dx, which is x cubed over 3, evaluated from -1 to 1, whatever. The rest is high school algebra. So the big idea is that here we're accepting a function as an input rather than a real number. So, okay, great. Now, how do we evaluate functional derivatives? Well, recall from the last lecture that a functional derivative is defined in the exact same way as the limit definition of the classical derivative. So, what is the classical derivative? Well, f prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. Exactly similar to that, exactly similarly, the functional derivative of a functional, okay, or we write it as delta f with respect to a function, okay? We're not calculating the derivative with respect to a number. No. Or with respect to a variable. We're taking the derivative with respect to a function, right? That's the key idea. And here we're taking the limit as the deviation from the true path. This deviation epsilon approaches 0 of what? Well, we're going to evaluate the functional at the fake path. Okay, how's that look like? Well, that's going to be f of x plus epsilon delta x minus x naught. Okay, so we're evaluating our functional at the fake path minus our functional evaluated. Let me use curly brackets just to be consistent. Evaluating our function at the true path, and divide all of this by epsilon. So that's how we take functional derivatives. It's also, I think, called the Gauss derivative, or whatever it's called. So now let's take the functional derivative of this most basic functional. So just to give you one more example of how to take functional derivatives, although we did in the previous lecture. So let's apply that maxim over here. So delta j of f with respect to delta f of x is equal to the limit as epsilon approaches 0. And here I'm going to have, let's see, the integral of -1 to 1 of the functional. So that's going to be f of x plus epsilon delta x minus x naught minus f of x dx, and close brackets. Okay, great. So I'm evaluating my functional at the fake path, or the deviated path, and the true path. So f of x and f of x cancel out. I'm left with epsilon, but of course, remember, all of this is divided by an epsilon. So this epsilon and this epsilon cancel out. The limit goes to hell as a result. And so I simply have the integral. This is simply the integral of the Kronecker delta of x minus x naught dx from -1 to 1. And what is that if not 1 if x naught is between these limits of integration, -1 and 1, and 0 otherwise. Otherwise, the Kronecker delta will evaluate to 0. So this is a simple example of a functional derivative. Now, we've taken a look at two more advanced functional derivatives. The first one, let me call it, I've already used j, let's say n of f of x. Let's say you have some kind of a power function. So the integral of, let's say, f of, in fact, instead of a function of x, let's say it's a function of y, f of y to the p times phi of y dy. And what we'd like to do here is evaluate the delta, the functional derivative of this functional, delta n of y, n of f, okay, with respect to a function f of x. And so we calculated in the previous lecture, you can go watch that if you'd like, we calculated that this is simply equal to p times f of not y, we integrated out y. The Kronecker delta is going to replace that y, stick it in the gutter, put in an x. So this is going to be f of x to the p minus 1. Kind of similar to the power rule, but that's not at all what's happening here, but it gives you a similar result. times phi of x. Okay, so that's that. That's the second functional derivative we looked at in the previous lecture. And then the third functional derivative we looked at is, let me see, I used J, I used N. Let's be creative. Let's use the letter K for our third functional. So for our third functional, let me try to recall. What did we have? Right. So we had a function of a function. So something like a chain rule. So let's say you have K of f of x is equal to the integral of j of f prime of x. Okay, dx. All right, so great. And you can put bounds if you like from a to b, whatnot. So the question is, what is the functional derivative of this? Okay, so taking the functional derivative of this does not look too bad. Let me just show you the first steps that we took previously, just so that you can remember kind of and gain some muscle memory. So the functional derivative is going to be delta k of f with respect to some function, right? We're always calculating these functional derivatives with respect to a function, not a variable or a number. So that is equal to, well, evaluate it at the deviated path. Okay, how's that look like? Well, that's going to be, first let me write the limit as epsilon approaches 0 of 1 over epsilon. And now I'm going to write the integral from a to b of g. Now here, let's see. First of all, what is f prime? This f prime here is just another way to write df dx. Slight typo. This should be f of y here. And I'm taking the functional derivative with respect to x. But the original functional is with respect to y, not x. Okay, so that shouldn't change anything. So far we have, let's see, 1 over epsilon, integral of g of f. So now here, f prime, remember, is df dy. So let me write d dy. But instead of f of, instead of f of y, I'm going to have f plus epsilon, all of that. So f of y plus epsilon delta y minus x. And that's it for this. And then I'm going to subtract the integral evaluated at the true path. So this is going to be minus g of df dy. And cap all of that off with an ending bracket, and we're done. Alrighty. So I might have missed out a dy at the very end, something like that. Okay, so very good. So this is our functional derivative, this entire mess. But at the end of the day, we actually got a very simple result. Let me write that down here. So all of this simplifies to, so the functional derivative, delta k, delta f of x, is equal to g prime of f prime of x. Okay, that was our end result. So these are our three main examples from the previous lecture. We've got delta k, delta f of x. We've got delta n, delta f of x. So that's right here. That's a kind of power rule example that we did. And finally, our most basic example was this one, where we had delta j, delta f of x, kind of gave us a Kronecker delta result over here. Okay, great. So all of this is all nice and fine, neat and dandy, but how is this going to be helpful for us? Well, take a look back at our potential energy right here. The potential energy is actually very similar to this last example that we did here, g of f prime of y, right? So we can actually evaluate the potential energies change if we perturb the true path a little bit by using this third example. Okay, so let me illustrate that right here. So if I have an eraser, which apparently Brown, okay, I was about to say Brown could not afford an eraser, but in fact it can. So we have, this is our average potential energy, right? And let's compare it to this k functional. So k is the integral of g of f. dy. And so you can see that these two integrals are very much similar, right? These two functionals are almost the exact same. So it stands to reason that the change in our potential energy, okay, the change in our potential energy, if we perturb our path, should be given by this last functional derivative. So what is that? That's g prime of f prime of x naught. So over here, I'm just going to write 1 over tau and v prime of x naught. Okay? And that right there is how much the potential energy changes if I perturb the true path by a small amount epsilon. Now we're going to look at calculating one more functional derivative, which is going to be really helpful for deriving the Euler-Lagrange equation. Let's check it out. Right, so here is the functional, which we're tasked with taking the functional derivative of. So let's see what we've got here. We've got j, okay, that's the name of our functional. We've got the curly brackets to indicate that the input is going to be a function f. And this is equal to an integral of g of f prime dy, where f prime is just the derivative of some function f with respect to y. Okay, so makes sense. Okay, looks good. How do we calculate the functional derivative of this? First things first, let's write down the definition of the functional derivative. So delta j of f with respect to some function f of x is going to be the limit as epsilon approaches 0 of our functional evaluated at the fake path. So f of x plus epsilon delta x minus x naught minus our functional evaluated at the true path, f of x, all divided by epsilon. It's always good to write that out. Always a good exercise to just remember and rinse it and repeat it once more. So let's take a look at how we can apply this functional derivative equation over here. So I'm going to first write this is equal to, so delta j of f with respect to some function f of x is equal to the limit as epsilon approaches 0 of what? Well, first of all, let me pull out the 1 over epsilon, and let's put all of this in braces. So I have the integral of g of what? Well, instead of f prime, I'm going to write d dy. Okay, so, but I don't just have f, right? I have f plus epsilon delta. So this had better be f of not x, actually. Here the variable is y. F of y plus epsilon delta y minus x. Okay, great. So that is my input for the fake function. Okay, I mean, we're evaluating the functional at the fake path, and then minus, what do we have here? So we have minus g of, well, this is just f of x, so this is straight going to be df dy. All right, and what is my integration variable? Dy. And I'm going to cap all of this off with a square bracket. Okay, good. So there you go. Not too shabby so far. So now what I'm going to do is, let's just go ahead and apply the derivative here. So this is going to equal, hopefully you can still see what I write here. I have the limit as epsilon approaches 0 of 1 over epsilon, and the integral of g of f prime of y plus epsilon delta prime of y minus x, because I just applied this derivative, and cap that minus g df dy all times dy, right? So here is my whole integral. So now the next step of the process is to stare at this and think about what to do next. So let's take a look at this. Now the first thing you might think is, hey, I've got a g df dy prime, and I've got something similar here, right? F prime. Actually, this is the same thing. You might as well write it like that. So this is just f prime. Now, if only I could exploit it. Let me write it as f prime of y. If only there was a way to cancel these out. The only thing is that this input is much more than f prime of y, right? Well, it's not if you make an approximation, right? If you make an approximation, then what is this? Using a Taylor approximation, f of x plus h is equivalent to, or approximately equivalent to, f of x plus h times f prime of x. And thus, in the same vein, g of f prime plus epsilon delta prime is equivalent to, or approximately equivalent to, g of f prime plus epsilon delta prime times g prime of f prime. So I'm going to go ahead and replace that over here. So coming over here, the limit as epsilon approaches 0 of 1 over epsilon times the integral of g. Now I'm going to put this here, g of f prime plus epsilon delta prime g prime of f prime minus g of f prime all times dy. And now you can see g of f prime and g of f prime cancel out here, right? So these cancel out. And so we're left with the limit, hopefully you can still see down here, as epsilon approaches 0, 1 over epsilon of the integral epsilon delta prime of x, oh, not x minus y minus x, the other way around, y minus x times g prime of f prime of y dy. Okay, very good. And so we're almost at the finish line. Now 1 over e times e kills the limit. And so we're left with, let's see, where should I write? Let's write over here. So we have, this is equal to, the functional derivative is equal to the integral of delta prime y minus x times g prime of f prime of y dy. Now looking at this, it might not be obvious what the next step is. In fact, it is not obvious to me. But when you have two things that are multiplied together and you're taking their integral, well then more often than not, the good thing to do, the best thing to do is integration by parts. And in fact, that's the right strategy here. So we're going to do integration by parts here. And how are we going to do it? Well, since I have literally no idea how to take the derivative of a Dirac delta function, I'm going to make that my dv so that the derivative gets killed, and this my u. So now I can say that du is simply going to be what? Well, it's going to be d dy of, here I have, first of all, what is this? G prime. So this is dg of f, so dg, where g is a function of f, df. Okay, so that's that. And v is simply going to be the regular Kronecker delta, delta y minus x. So now applying integration by parts, this is going to give me u times v. So u is g prime of f prime times v, so delta y minus x. Okay, so that's my u times v minus the integral of v du. So I have v, which is, once more, delta y minus x times du. What is du? That's this mess over here, d dy times dg of f with respect to df, and all integrated with respect to y. So now looking at this, it might not be immediately obvious what's happening here. Let's see what's going on. We've got g prime of f prime delta y minus x. All right, okay, that's reasonable. And then all we did here was u times v after all. And remember that we are to evaluate this at the endpoints of whatever path we're taking. And we're subtracting from this the integral of delta y minus x times dv, times du rather. So we have this over here. Now, if you stare at this for a moment, then it might strike you that, wait a second, this is a Kronecker delta. We're integrating with respect to y here. So really, we're just trying all the values of y until this integral is non-zero. And that only occurs when y is equal to x, right? And so that's going to tell us, first of all, at the endpoints, I know that my deviation from the true path is 0. So this right here is 0. And so I'm left with, hopefully you can still see what I write here, I'm left with minus d dx of dg, which is a function of f, df. And so that is the result of my functional derivative. Okay, great. Now, one small caveat. This is not really a typo. It's just a convenience. So here my input I wrote was f, g as a function of f. Now, if you look originally, g was actually a function of f prime, not f. So really I should put f prime here. But regardless, f might have been the derivative of some other function. So in any case, my result stands. So now what we're going to do is take a look and see, why is this useful? Why did we bother going through all of this calculus of variations? Well, the reason why is because now we can see, we already saw how our potential energy responds to a small change in our true path. Now we can see how the kinetic energy responds. Recall that the kinetic energy T, the average kinetic energy T, is 1 over tau times the integral from 0 to tau of 1/2 m x dot squared dt. Right, that's our kinetic energy, right? Just 1/2 mv squared, just a fancy way to write that. Now, how does this change? What is delta t, which is a function of x? What is delta t with respect to delta f of x? How does our kinetic energy change? Well, now we can simply use this result over here. Let me write this nicely here. This is such a big result. So this result is very important, in fact. This result was the functional derivative of j, the functional j, with respect to some function f of x. And this is what we obtained. So now we're going to use this to figure out how our kinetic energy responds to a small change in the true path. So this is going to be minus d dx, so minus d dx. And here I ought to be a bit careful here, you see, because here I'm trying to see what happens if I change my path, a little bit. So it's not going to be the functional derivative with respect to f of x. No, it's going to be the functional derivative with respect to x of t. That's the key. All right. So instead of d dx here, I'm going to have minus d dt. Alrighty. And then here I'm going to have, okay, the integral of dg. Now, of course, I don't have a g here. Here I'm going to have what I have here, x dot squared. So I'm going to have d dt of x dot of t squared. And I just factored out this 1/2 m and the 1 over tau. I just factored those out. Those are just constants anyway. So what does this evaluate to? Well, this is going to be 2x dot. Okay, so this is going to be minus d dt. So I have 2x dot times 1/2 m 1 over tau. So 2.5 cancel out. And then I have d dt of x dot, which is just x double dot. So I have minus mx double dot over tau for the change in my average kinetic energy as I perturb from the true path slightly. So this is fantastic because now I have the deviation in both my potential energy, V of x, so delta V, in my average potential energy at least, delta V of x. So how does that respond to a small change, to a small perturbation? Well, that is, let's see, this is, let me look back at what we got for that. So we obtained V prime of x, V prime of x. And here we obtain the kinetic energy's response to a small perturbation. So now this is great because now we can figure out, well, how they respond, right? We see how the kinetic energy changes, how the potential energy changes. We're done, right? No, not quite. In fact, if you look at this for a second, something might strike you as odd. See, look at how the kinetic and potential energy change. What if we subtract them? Take a look. What if we did delta t, okay, the average kinetic energy, delta x of t, minus delta v, delta x of t? What would we get? Well, we would get, let's see, we'd get this right here. So minus mx double dot over tau minus v prime of x over tau. Well, factoring out the 1 over tau, I simply have minus mx double dot minus v prime of x. But hang on a second, doesn't Newton's second law tell us that F equals ma is equal to the gradient of the potential, right? So actually the negative gradient of the potential, sorry. So if mx double dot is the negative gradient of potential, that means this thing right here is 0, right? Because just plug it in here, you get 0. So what does that mean? That means we've got some kind of a special quantity right here when we subtracted the kinetic and potential energy. In fact, that special quantity is no more than the Lagrangian. It's the kinetic minus the potential. And in fact, if we integrate the Lagrangian over time, then we get the action, which has units of energy times time. Okay? So now what we're going to be able to do is from what we've just gotten, we're going to derive the Euler-Lagrange equation and then subsequently the Klein-Gordon equation. So let's go ahead, hit the board. All right, folks, the time has come for arguably the bestest or the greatest part of this video so far, which is to derive the Euler-Lagrange equations from calculus of variations. So let's get to it. So first thing I'm going to do is write down the action. The action S is simply the Lagrangian L integrated over time. It's L dt. Now the Lagrangian, we know, is a function of not only the position coordinates q, but also the momentum coordinates q dot. Okay? So now if we want to demand that the action is stationary, that we have a minimum action, then what we really want is for delta S, delta f of x to be 0, right? So let's do that. Let's enact that over here. Instead of q and q dot, I'll use x and x dot. So don't shoot me in the face. So we're going to have delta L, actually instead of f of x, we're evaluating the change in the action. We're demanding that the action be stationary with respect to x of t, which is some parameterized path. Okay? So delta L with respect to delta x of u, delta x of u, delta x of t, plus delta L plus delta x dot of u, delta x dot of u, delta x of t. Now, for those of you for whom this looks very foreign, no worries. This is just the multivariable chain rule in action here. In fact, if I maybe just write this as L as a function of x and x dot dt, maybe this will look a little less foreign. Or maybe if you just look at this for a minute, maybe if I just delete this denominator here and make these vanish as a result, maybe that'll look less foreign because all we really have is the multivariable chain rule. For example, if I even have a function like f of x comma y, then what is the total differential of that function if not partial f partial x dx plus partial f partial y dy? Exact same thing here. Total change in our action is partial L partial x dx, partial L partial x dot dx dot. All we're doing here is demanding that this action remains stationary with respect to x of t, and hence these extra denominators right here. Okay, so that's all we've got so far. Scratching my head because I don't know what to do next, but let's stare at this for a second because this itself is nice to look at. So the next thing we might want to do is, first of all, integration by parts may be an option to evaluate this integral, but that doesn't seem likely here. Let's see, what can we do? We want to demand that this thing right here is 0. Okay, we want the action to remain stationary. Well, I do know one thing, right? I know that delta x of u over delta x of t, what is that? If you watched the previous lecture, then you know exactly what it is. Just by knowing, even if you didn't watch the previous lecture, what is dy over dx? That's just 0. What is dx over dx? That's just 1. And so if you have an arbitrary coordinate, delta xj over delta xi, what is that? Well, that's the Kronecker delta of I and j, meaning that if the two coordinates are the same, then you have 1 and 0 if they're different, right? And of course that makes sense. And so if we extend this to calculus of variations, what that says is delta y over delta x is simply the Kronecker delta of y minus x, okay, something like that. And so delta x of u over delta x of t, that's just going to be the Kronecker delta of u minus t. And similarly here, even though there's an x dot here, I can just pull out that x dot as a d dt and then write the same thing, delta of u minus t. And so my action over here becomes stationary as follows. So I have delta s, delta x, I should really write the delta as a delta, x of t is equal to, I have the integral of, wow, I keep wanting to write partial, delta L, delta x of u times the Kronecker delta of u minus t plus the Kronecker delta of L, delta L, delta x of u, not t, but u. And then I finally have this over here, d dt of the Kronecker delta of u minus t. And all of this is with respect to, I forgot to even write what it's with respect to. I believe we're integrating with respect to time here. Okay, so wonderful. So we've got all of this over here. Now, the next thing we're going to take a look at is, this should be a du here, integrating with respect to u, so that we're left over with a function of time at the end for the change in the action. So looking at this, what's our next step? Well, one thing we can do is break up the integral into these two pieces and try to evaluate each of them separately. And as a matter of fact, that's what I will do. So, but before I do that, let's just take a look over here maybe. If you look over here, notice that this is simply the integral of some function times the Kronecker delta. And we're integrating with respect to u, meaning we're trying all the possible values of u until u equals t, at which point this argument of the integral is not 0. And so the integral of this right here is simply the same thing, but with u replaced by t, because that's the only possible value for the argument where it's non-zero. If u was not equal to t, then the Kronecker delta would kill this argument. So we're going to have delta L, hopefully you can see down here, delta L, delta x of t times, oh, well, I suppose that's it. That's all there is to it. Okay, and now I have this plus the integral of delta L, delta x dot of u times the derivative d dt of delta u minus t du. And of course, all of this is equal to the change in my action with respect to some parameterized path x of t. Okay, great. So now I can go ahead and put my mathematical magic to work by working on this second integral right here. So let's do that. So let's just focus on that second integral for a second. So I have the integral of delta L, delta x dot of u. So delta L, delta x dot of u times d dt times d dt of delta u minus t, all times du. All right, so wonderful. I've got this right here. Now the question is, all right, great. How do we even handle this? Well, you could use integration by parts. So you can make this your u, this your dv, and so that means v is just delta u minus t, and du is, well, we're using u here, so maybe du is going to be d du of partial L, partial x dot of u. Okay, so maybe something like this. And so now we can just apply integration of parts. Quick typo there. There should be a T, not a U. And so now let's go ahead and apply integration by parts. So this right here is U times V. So delta L delta X dot of U times V, evaluated at our endpoints for the path, minus the integral of V du. So V is delta U minus T times du, which is, where is du? So I have U times V minus V du over here, d dt partial L partial X dot of U. Alrighty, so we've got all of that, and so now don't forget your du out here at the end. So now we can go ahead and evaluate all of this mess. So first thing I'd like to point out is that at the boundaries, first let's see what we have here. We have delta U minus T d dt. Okay, so at the boundaries, our deviation from the true path will be 0. So this right here evaluates to 0 for that reason. And now focusing on this right here, what do I mean, by the way, that at the boundaries the deviation is 0? I mean that, for example, let's say that this is the true path from point A to point B in phase space. And let's say we take an alternative path, right? But at the endpoints, at these endpoints, T sub I and T sub F, that variation has to die, right? Because the endpoints have to match. And so that's why this right here, this term dies out, because at the endpoints, this term has to die out. Okay, so this is equal to, let's see, minus, and this Kronecker delta is going to force this U to be replaced with T. So minus d dt of partial L partial X dot of T. Now, don't forget, this integral was just the second part of this whole shebang, right? Our first part was partial L partial X of T. So that means the change in our action, delta S delta X of T, is partial L partial X of T minus this new integral result, minus d dt of partial L partial X dot of T, and of course the action must be extremized, and so this is 0. And seems like part of this got cut off from the screen, so let's show the viewers what our biggest result is. So in summary, that means we have just derived the Euler-Lagrange equation as follows: partial L partial X of T minus d dt of partial L partial X dot of T is equal to 0. And this, ladies and gentlemen, is the Euler-Lagrange equation derived from no more than the calculus of variations. Right, so the next step is to introduce something called the Lagrangian density. So of course we know that the action, right, S is equal to the integral of the Lagrangian over time. Now the Lagrangian density is simply what it sounds like. It's a density of the Lagrangian. So it's something like this. We write it as follows. It's a curly L, okay, d cubed x dt. So basically it's just like a regular density. If we multiply a volume times the Lagrangian density, we get the regular Lagrangian. Okay, so this is still equal to the action. Now, what I'm going to do is, let's say that the Lagrangian density, let's write it as follows. I'm going to say it's a function of, as usual, x and x dot d cubed x dt. Now what I want to show you is something that's really cool. First of all, we figured out that the action principle dictates the Euler-Lagrange equation to be dl dt minus d dt. Oh, this should be dx. Oops. dl dx dt dl dx dot is equal to 0. Of course, some of them should be partial, but whatever. So now, just in direct analogy to this, we can straight up write the 4-vector form of the Euler-Lagrange equation as follows. I can write partial the Lagrangian density, partial phi, minus, let's see, now this here I'm going to write as the 4-vector derivative of partial L, okay, my Lagrangian density, partial mu phi. Okay, something like this. This is equal to 0. Now we can use this to figure out what the Klein-Gordon equation is. So here's how we can do that. So first of all, let's say we have a Lagrangian of the following form. Let's say it's 1/2, okay, partial mu phi squared. So this is kind of like 1/2 mv squared, okay, minus, now I need a kind of potential energy term that looks like a harmonic oscillator. So I'm going to write 1/2 m squared, let's see, and phi squared. Okay, let's just double check that that's correct. Yes, indeed. So now we're going to compute the different derivatives. Let's compute partial L, partial, let's first do this derivative here. Partial L, partial mu of phi. And what is this equal to? Well, I've got a mu of phi right here, so that's going to bring down a 2 over here and leave me with partial mu of phi, where I have a contravariant index here for a reason. You'll see very shortly why it's contravariant and not covariant. And let's evaluate this derivative here. Partial L, partial phi. Bring down the 2, that gives me minus 2m squared phi. Okay, that should be right. Oh, it's not right because there's a half, so just minus m squared phi. Okay, and so now let's plug all of this into the 4-vector form of the Euler-Lagrange equation. So partial L partial phi is minus m squared phi, and partial mu of this is minus partial mu of phi, and this is equal to 0. And voila, if I now go ahead and factor out phi, look at what we have here. This right here is no more than the Klein-Gordon equation. And there you go, ladies and gentlemen. That's how you use calculus of variations and the action principle to derive the Klein-Gordon equation. So thank you for watching this episode of Advanced Quantum Mechanics. Hopefully it was advanced enough for you.